Hello, welcome back to Digital Urim. In the previous video, you learned what an operating system is and why it is the real battlefield of cybersecurity. Today, we are crossing an important boundary. We are going inside the operating system. Until now, we talked about the operating system as an administrator, but today we will understand its internal structure. Because many modern attacks do not occur on the interface. They occur inside the system, deep within its internal layers. Today you will learn three fundamental concepts: kernel, user space, system calls, and most importantly, you will understand how these concepts allow programs to interact with hardware. One of the most common mistakes when learning operating systems is believing that applications interact directly with hardware. But that is not true. Applications cannot directly access memory. They cannot directly write to disk. They cannot freely control the processor. If they could, systems would be unstable, chaotic, and extremely insecure. That is why a critical component exists, called the kernel. The kernel is the core of the operating system. It is the most critical component. Everything that happens inside a computer passes through the kernel. When a program needs memory, the kernel decides. When it needs CPU time, the kernel assigns resources. When it needs to access a file, the kernel controls that access. But the kernel does more than manage resources. It protects the system. It prevents malicious programs from directly accessing hardware. Without the kernel, there would be no real security. The kernel controls several critical components. One of the most important is processes. Every program you run becomes a process. The kernel decides which process runs, how long it runs, how much memory it can use. This is known as process scheduling. Now imagine this: malware creating hundreds of fake processes that could slow the system, consume resources, and hide malicious activity. All of that happens under kernel control. User space is where applications live. Your browser, your text editor, your terminal, your security tools, all of them live inside user space. But there is a critical rule. Applications cannot directly access hardware. That would be extremely dangerous. Imagine a malicious program accessing memory directly. It could overwrite system data. It could corrupt processes. It could even crash the system. That is why the kernel acts as a guardian. Every request made by an application must pass through the kernel, and the kernel decides what is allowed and what is blocked. System calls are requests made to the kernel. They are the mechanism that allows applications to interact with the operating system. When an application needs to perform an action, such as reading a file, sending data over the network, or creating a new process, it does not do it directly. Instead, it makes a system call. A system call is like asking permission. The application sends a request. The kernel receives that request. It validates it, and then decides whether the action should be allowed. This happens thousands of times per second, without the user even noticing. But from a cybersecurity perspective, every system call represents an action that can be monitored, and every monitored action can reveal suspicious behavior. Let's visualize the complete flow. An application wants to read a file. First, the application creates a system call. That request is sent to the kernel. The kernel checks permissions. It verifies whether the process has access rights. If permission is granted, the kernel accesses the disk. It retrieves the requested data and returns the result to the application. This flow happens constantly, thousands of times per second. Every time you open a file, every time you launch a program, every time your system connects to the network, and every one of these operations can be monitored, logged, and analyzed. This is exactly how security monitoring works at the system level. Now let's imagine a real attack scenario. A user downloads a file. The file looks harmless, but it contains malware. When executed, the malware runs inside user space. But the malware wants to perform dangerous actions. For example, modify system files, access sensitive data, or create hidden processes. To do this, the malware must use system calls. It cannot bypass the kernel. And this is where modern security tools become powerful. EDR systems, endpoint detection and response tools, monitor system calls. They analyze patterns. They detect abnormal behavior. And when suspicious activity is detected, they generate alerts. This is how many real-world attacks are detected today, not by file names, but by behavior. A cybersecurity analyst does not only look at files, they look at behavior. They analyze processes. They observe memory usage. They monitor system calls. Because behavior reveals intent, malware may hide its files. It may disguise its name, but it cannot hide its actions. Every action must pass through the kernel, and every action leaves traces. This mindset is what separates beginners from professional analysts. Today, you learned something fundamental. The kernel is the core of the operating system. User space is where applications live, and system calls connect both worlds. But now, a critical question emerges. Who is allowed to make these calls? Can every user perform the same actions? Or are there different privilege levels? In the next video, you will learn about users, privileges, and the root user in Linux. This will be one of the most important topics for understanding real-world attacks. Understand, defend, grow.